What's happening, everybody? Can you hear me?
Yes.
I had a little weirdness with my microphone. So, what's happening? Nothing, apparently, huh?
Nothing.
Bored yet?
Oh, tired. You're tired.
You're still working, right?
Oh, yeah.
All right. So, what do you guys want to do? Math.
Got that.
How are the eigenvalues and eigenvectors and diagonalization stuff going? So before I move on to the next thing, we may as well make sure that you're comfortable with that. When's the homework due? I forgot. It's available, right? The diagonalization homework? Yeah, so that's homework 10.
Yeah, it's due today.
It's due today? Okay. Well, good chance for you guys to answer questions. How's it going?
Good, I finished it.
Good?
Mm-hmm.
I think we're still waiting for everyone to kind of file in. Oh.
All right, shall we just move on?
Sure, why not?
Yep.
Okay.
Mm-hmm.
Let me grab a pencil.
What do I got here? Whiteboard. There we go. Okay, so today we're starting a new chapter. So we are actually done with eigenvalues and eigenvectors. We just do the first 3 sections. Okay. Sometimes, some years, I actually do, I think it's 5-4, which is complex eigenvalues and eigenvectors. I would rather move on to this stuff, the dot product, because it's more useful. I doubt any of you are ever going to see complex eigenvalues and eigenvectors in your lifetimes. Could happen. I could be wrong, at which point just call me up and make fun of me or something. Okay. But I think the dot product is more useful. So this is chapter 6. Let's see. So this next week's the last week. So today I think we can get through 6.1, and I always say maybe into 6.2, but I never go as fast as I think I will. I'm pretty sure we can comfortably get through 6.2. I don't know about 6.3 or not, so we'll hold off on that. I don't want to I want to at least leave next Thursday for you guys to answer or ask any questions that you have. So I don't want to be like teaching new stuff right up to the last minute. So let's see how today goes, and then so we're either getting through 6.2 or 6.3. Okay. All right. So chapters. Yo.
Now I know what we want to do.
What you want to do?
That I didn't even get to touch on. How can you tell eigenvectors span the same subspace?
Oh, that's right. Okay. So not even eigenvectors. What if I just give you a couple sets of vectors? Okay.
If they're linearly dependent, they should.
Yes. If you can make specific what you just said, which is linearly dependent on what else, then you're and other things are independent, you're in business. Okay. So let's say do the sets. Let's just do 2 vectors in R3. So I think I had like 1. I don't remember what I had before. Let's just make up some new stuff.
I've got those here.
Yeah, all right. May as well.
Yeah, 1, -2, 1, 3, 0, 1.
Hang on. 1, -2, 1, 3, 0, 1?
Yes. And the set 4, -2, 2, 1, 0, 3.
Close enough?
Mm-hmm.
Span the same. If I did this right, I think the answer is going to be no, but we'll see. Span the same sets, or the same subspace, let's say. Let's put it that way. Same subspaces.
And that's a subspace within R3, yeah?
You got it.
Cool.
Because that's where these guys live.
Bingo.
All right. So I've thought about this a fair amount. And I think what I have come up with is probably the best way of doing it. I don't guarantee it's the only. And I think probably there's some way I can kind of trick the matrix I'm about to show, the two matrices I'm about to show you, into actually giving up more information, but I've not yet figured out how to do it. So basically, what it comes down to is I need to show that, what do we want to call these? Let's call this like set A or something like that. So set A and set B. Okay. So basically, I'm going to show that the span of A is equal to the span of B. Or check and see, or decide that it's not, because it might not be, okay? Or decide it's not, okay? So I don't want to make this sound fancier than it is, but one trick to showing that two sets are equal in mathematics. So one way of showing that two sets are equal, and let's call them A and B, it's to do something that sounds stupid. So what you're going to show is that A is a subset of B. So in other words, everything in A is in B. Remember, that's our subset symbol. Not subspace, but subset. And then what you do is you flip it around and you show that the other thing is a subset of the first. Okay? Because if you have two sets, each of which is a subset of the other, so think about what this is telling us. So the first statement here, if we can prove it, says, well, if something's in A, then it's in B. And then the flip side is, well, if it's in B, then it's in A. If I can show both those statements to be true, then the two sets must be the same. Okay. So that's one common trick to show that two sets are equal in math.
Isn't that kind of a part of Gödel's theorem?
Of whose? Gödel's theorem?
Yeah.
Gödel's theorem's a little fancier than that. It probably rests on this kind of thing. Set theory gets really weird and makes my brain hurt.
Fair.
If you start digging too deep, you start to discover the fact that the universe can't exist and all this stuff, and it kind of is depressing.
Yeah, that is depressing.
Yeah.
Thank you, Bertrand Russell.
What's that? David, what'd you say?
Thanks, Bertrand Russell.
Oh, yeah. Yeah, paradoxes. I don't know. I used to love them, but I had to quit thinking about them. Okay, so what I'm going to do at a real high level, basically I'm going to row reduce two matrices, but let me explain why. So what I'm going to do first is I'm going to show that each of the two vectors in this B set is a linear combination of these two right here. What that will show me is that those two are both in the span of that. So every linear combination of the things on the right is also going to be in the span of that. That will give me one of these directions. Okay. Then what I'm going to do is I'm going to flip it around, and I'm going to see if each of these two vectors here is actually a linear combination of these two. If I can do it and they're linearly independent, which will come out of this thing, okay, then I'm in business. So to make a long story short, what I'm going to do is I'm going to row reduce two big matrices. So let me write them down first. So I'm going to row reduce what I get when I kind of do things in this order. 4 minus 2, 2, 1, 0, 3. Okay. And I'm kind of thinking about myself as augmenting that thing there and kind of solving it twice. And I got so organized, I put my calculator someplace I can't find it. So talk amongst yourselves for a second while I row reduce. 3 by 4 because I ain't doing this by hand. Okay, 1, 3, 4, 1. If I did this correctly or incorrectly, I actually just kind of made a guess in here at the end, and I think it's not going to be the same, but we'll find out. All right, so I have 1, 3, 4, 1, minus 2, 0, and 1, 1, 2, 3. Okay, so this thing reduces down to so this equals 1, 0, 1, 0, 0, 1, 1, 0, and 0, 0, 0, 1. Where again, if I'm kind of thinking about it as augmenting it, it would be there. Now talk to me about that. What did that just tell me? In particular, that 4 minus 2, 2, my third column vector there on the left, is that a linear combination of the two vectors on the, sorry, this one right here. This vector right there kind of corresponds to that guy. So judging by what came out, is that 4 minus 2, 2 a linear combination of these guys or not?
Yes.
Yes.
It is, because I can solve it, okay?
Right.
How about the far right one?
It is not.
It is not. That thing right there, the fact that that fourth column is actually a pivot means that that 1, 0, 3 vector points in a different direction than those two take up. If I try to think about, can I write 1, 0, 3 as a linear combination of those two vectors? That 1 there gives me a 0, 0. I'm kind of skipping over that 0 because I'm thinking about augmenting it and just solving it with that that column on the right. That tells me I can't solve it, okay? So the fact that that is a pivot means, since that's a pivot column, this vector, 1, 0, 3, is not in the span of that A set. Okay. So they can't those two sets of vectors I gave you can't possibly span the same region.
So it's linearly independent from the other.
From those first two. Yep. Okay.
Gotcha.
So if that happens, you can stop. They can't possibly span the same region. Now, let's do something where they do. So let's do this versus. So let's take my A set, my first set. Let's take it to be the same thing. So I have 1, minus 2, 1, 3, 0, 1. Set symbols. And now let's come up with a couple of vectors that do. So what I'm going to do is I'm going to add them. So I get 4 minus 2, 2. So you're watching me create a test problem in my head as I go. Now what I'm going to do is I'm going to take up some other linear combination. So if I take the second one and subtract the first, I get 2, 2, 0, I believe. Let me double check that. I think so. Okay. And I think, although we'll show it with a row reduction, that those two sets of vectors, A and B, actually span the same subspace. Okay. So the first thing I'm going to do is I'm going to take, like I did before, I'm going to line these things up with the A vectors first. 4 minus 2 and 2, 2, 2, 0. And I'm thinking about kind of augmenting there. So this thing row reduces to, I'll be with you in a minute. Second matrix, edit. Oh, I only change one thing, don't I? 2, 2, 0. Okay, so this row reduces to 1, 0, 1 minus 1, 0, 1, 1, 1, and 0, 0, 0, 0. Those are lousy zeros. Okay, so now talk to me. So that 4 minus 2, 2. Look at that, what comes out of the row reduction, and tell me whether or not it's a linear combination of the vectors in A.
It is.
It is.
It is, because the column that corresponds to it is not a pivot column. So if I just kind of, I just held my hand over my pad like it's going to keep you from seeing what you're looking at. If I kind of eliminate that third column and just solve the rest of it, yes, I can solve it. Okay. How about the fourth column? How about the 2, 2, 0? I can solve that as well. I just kind of forget about the third column and look at what's left. Yeah, I can do that. Okay. So the fact that neither of these is pivots, neither is a pivot, that implies that the span of B is a subset of the span of A. Now there's one subtle point here that I can't just jump to, and I can't just jump to saying the spans are equal. So what I've just done is I've shown you that the 4 minus 2, 2 and the 2, 2, 0 are both in the span of those vectors in A. But what do I still have to do? First off, are the vectors in A linearly independent?
Yeah.
They are, okay? So in order to span that same thing, I have to have at least 2 linearly independent vectors, correct? So the one kind of hang up that I can't figure out how to get around without doing this again, and I'm sure there's some clever way of doing it, is that this one row reduction does not tell me when these 2 vectors here are linearly independent or not. There's nothing I can look at over here in the row reduced form and say, yep, they're linearly independent, so we are good to go. You can look at them and tell, but if I had a whole bunch of vectors, like 15 vectors and, you know, an R15, this, or R16, this will get a lot harder. Okay. So what I can do is I can then flip it around. Okay. Then I can do this. All I'm doing is kind of putting the B vectors first. Okay. And row reducing this thing. All right. Okay, what do I got? 4, 2, 1, 3. Minus 2, 2, minus 2, 0, 2, 0, 1, 1. All right, 4, 2, 1, 3, minus 2, 2, minus 2, 2, 0, 0. Okay, looks good. All right, and this thing gives me 1, 0, 0, 0, 1, 0. And by the way, what do I now know about those 2 vectors in B? Since when I row reduce, they both end up being pivots, I do now know that they are linearly independent. Okay, and here I get some weirdness. 1/2, 1/2, minus 1/2, 1/2, 0, and 0. Okay, the fact that neither of those is a pivot column, this implies, or I should say neither is a pivot. Implies, oops, sorry, too far. Let me see if I can fix this. There we go. That implies that the span of A, those things on the right, is actually contained in the span of B. Because what this tells me, since neither the third nor the fourth columns are pivots, is that these 2 vectors over here that I started with, both of them must be linear combinations of these 2 as well. So all the linear combinations of these must also be linear combinations of those. They're not getting me any place new. Okay, and this right here on the left tells me that those B vectors are linearly dependent. Well, I guess I don't really, I kind of get that for free in this case. If I'm looking for a basis, I need them to be linearly independent. But in any case, I think what I have done now is sufficient, because what I have done is I've shown that the span of A is contained in the span of B, and the span of B is contained in the span of A, so A and B must be the same set. or the spans of A and the spans of B must be the same set. So it comes down to 2 row reductions, flipping that thing around and just making sure that the third and the fourth columns, in this case, are not pivot columns. Because that's telling you that B, the vectors in B are getting you the same places that A is, and then you flip it around and say the vectors in A are getting you the same places that B is.
I'm a little bit late. Is this what we were supposed to be pondering?
This is the ponder. Yep.
Okay.
And let me go back up here and see if I can contrast this with the one. All right, so let me do one last example here, if you don't mind. Okay. So one last kind of possibility. So one more versus. So let's take A is equal to, I'm just making this up as I go along. I wonder what's going to happen. Let's do this. Oops. Let's keep
Is
our
this a need to know? Should I go back and, sorry.
What's that?
Is this a need to know? Should I go back in the video later and take notes on this?
Yeah, you don't need to know it, no. And let's say B is, so watch what I'm going to do here. I'm going to add, oh, hang on, I kind of switched around. This will work. So if I add them, slightly different example, 0 and 2. So what I did was I added them, okay? And watch this. Nothing up my sleeve. What did I do there?
You multiplied the 3, 0, 1 vector by 2 and then by 4?
Right. In fact, I forgot all about the 3, 0, 1 vector, and I just added the 2 vectors in A to get the 6, 0, 2, and then I just multiplied it by 2. So what I did here is I gave you a set that's not linearly independent. Okay. This set is, so they can't possibly span the same thing, but let's see what happens. So if I row reduce this guy, six, 0, 2, 12, 0, 4. I'm just doing this to prove a point as to why I can't figure out how to do it in like one step. So this thing reduces to, oh, that'll work. Okay, 6, 12, 0, 0, 2, 0, 4. All right, so my A is 4, 2, 6, 12 minus 2, 2, 0, 0, 2, 0, 2, 4. Okay. So when I row reduce this guy, I get out 1, 0, 1, 2, 0, 1, 1, 2, and 0, 0, 0, 0. Okay, so what does this tell me? So my 0, 2 vector, is it in the span of those vectors in A? Look at my third column.
What is the condition, again, that we need for them to span? I didn't catch the last page.
I want to see if these two, if the sets of vectors A and B both span the same set or not.
Yeah, what is the condition for the row reduced?
I'm trying to show that every vector in B is in the span of A, and that every vector in A is in the span of B. If I can do that, then I think they're the same. I don't think, I'm sure they're the same. Okay. So basically, I'm doing it all at once. So I have that 6, 0, 2 vector, and I want to see if it is a linear combination of that 4 minus 2, 2 and 2, 2, 0. And then I want to do it with 12, 0, 4 as well.
Okay.
So what this tells me is that it's consistent for both of them. Okay. So both, geez, I wish I'd labeled these. So this says 602 and 1204 are in the span of those A vectors. Okay, so the span of the B vectors is in the span of A. Okay. Now, what kept it from being, so the first example I did, they were not equal. What kept that from being the same is that here, the third and the fourth columns ended up being, one of them was a pivot column, which meant I couldn't get there. The corresponding vector was pointing in a completely different direction. And that meant that I had something in the B set that couldn't possibly be in the span of the A. Okay. So as I'm looking at this, I'm almost wondering if I can answer my own question, but it's not clear to me that even though I can solve both these things, maybe that does do it. 1 and 2, no, not quite. This here, I can't look at that and tell that the third and the fourth columns are actually multiples of one another. Because this thing kind of stops pulling out linear dependence relations as soon as it kind of runs out of pivots. And I just don't see that linear dependence in this case actually showing up in those last two columns. Okay, there must be some trick or some way of looking at this and telling, but I don't know what it is. But what I would do in the next part is I would then look at the other side. So then I would just flip it around and do 602, 1204, and then I want to see if the span of that includes these two vectors in A. Okay, and I'm pretty sure it cannot, even without row reducing, because tell me something about the second row. If I take linear combinations of 602 and 1204, I can't possibly get to stuff whose second component is anything but 0. Right?
Right.
But let me go ahead and do this. Be with you in a second. 6, 12, 4, 2. 6, 12, 4, 2, 0, 0, minus 2, 2, 4, 2, 0. Okay. And this thing row reduces to 1, 2, 0, 1. And I'm kind of thinking of that as my augmentation. 1 minus 1 and zeros. Okay. And what is that telling me? That is telling me right there that that third column, because it's a pivot, it's telling me that 4 minus 2, 2 is not a linear combination of those things right there, as promised. Okay. So third column is not a linear combo of vectors in A. Or is that B? That's B, I guess. I did it backward. Okay. So that's telling me that the span of A is not a subset of B, because there are things in A that are not contained in B. So the two sets are not the same. Okay. I don't know of any quicker way of doing it. So in general, excuse me, if you want to decide if two sets of vectors span the same subspace or not, you just line them up in an augmented matrix with a line going down the middle, and you row reduce. Okay, but you have to do kind of both sides. Okay, put your A vectors on the left, your B vectors on the right. If you only end up having pivots on the left, then you're halfway there. Then you flip it around and do the B vectors on the left and the A vectors on the right. If you only have pivots on the left, then you're done. Then they're the same space. They span the same space.
Is this one of your lemmas, or is this
I could not find this on the internet. I didn't look too hard, but I could not find anything better. So I'm not going to take the credit for it, because I'm sure people know how to do this. But, you know, I got to the point where I saw people fighting about it and read it, and I thought, I've had enough.
Fair.
All right, so good question. Good final exam question.
Not need to know, huh?
Yeah.
No, I would not spring this on you in the final. No, it is. I guess it's not a out of the realm question. I mean, we've been talking about spans and subsets and all that stuff, so it's kind of a natural question.
Kind of a combination of things we've learned thus far, anywho.
That's right. Okay, anything else on diagonalization or anything?
Yeah, I think I'm all right.
So initially, I think that whole issue came up because of the wacky way in your homework that they actually came up with some eigenvectors.
Yeah.
At first, I thought, you just have to decide if these two eigenvectors span the same space as the two eigenvectors that you came up with using like our algorithm. But in general, I think I decided that at least in all the options they gave you, there's a better way of just eliminating some options and then going by just what your eigenvalues are, and that rules out all your other answer options, which is easier than this, I think.
Mm.
Little.
But not nearly as instructive. Okay, we ready for chapter 6?
Heck yeah.
Yeah, that's what I like to hear. All right, chapter 6. Where are we at there? Oh. I'm trying a new setting that turns turns my C's into, okay. I couldn't do it when I tried, but now it's going to turn my C's into circles. Chapter 6. Chapter 6, what's it called? The dot product? There's a product of vectors. It's a vector product that goes by 3 different names. Okay. The dot product.
It's called, I can tell you right now, it's called orthogonality and least squares.
Oh, none of the above. Okay. Other stuff. Okay. So we're going to start out with the dot product, which also goes by the inner product and it also goes by the scalar product. Okay. Honestly, it goes by all 3 names. They have slightly different connotations, but we don't have to worry about it. In R2 and R3, you kind of call it the dot product, although if you used any one of these terms in any math paper, everyone would know what you're talking about. So in R2 and R3, they kind of call it the dot product. In like higher dimensions where it doesn't have as much a geometrical significance, it's kind of called the inner product. Scalar products kind of, I guess, getting old-fashioned, but it's there as well. Okay, so what it is, the dot product is a way of multiplying 2 vectors together and out pops a scalar. It's a number. Okay, so the dot product of 2 vectors okay. And the notation for this, wait for it, it's a dot. Okay. It is a type of multiplication. Okay. So if we have 2 vectors, x and y, the dot product is a scalar. It's not another vector. Okay. And the way you find it is very straightforward. And it's easy. And it's defined as, okay, so if I have, let's do it in 2 dimensions, I'll just make it easier. So if I have an x vector with 2 components, x1 and x2, and I'm taking the dot product with my y vector with components y1 and y2, okay, blink and you'll miss it because it's really easy. All I do is I multiply my first components together. I multiply my second components together and I add them. That's it.
Oh.
Okay. 2 multiplications and an addition. Now, if I had vectors in R3, what do you think I would do? I just have one more product at the end there to do, right? So if I had, so this is, I guess, in R2. In R3, it looks exactly the same. You just have one more term you got to fight with. And fight's kind of an exaggeration because it's not really much of a battle. Equals, oops, I don't want to, it's not a vector. Forget you even saw that. X1 plus X2, Y2 plus X3, Y3. Okay. So what we're going to see is that in R2 and R3, this dot product, surprisingly, because it looks so darn simple, actually contains a lot of geometric information. And by geometric information, I mean there's lengths and there's angles hiding in this thing, which is kind of surprising to me. Okay. In, you know, R4, R5 or whatever, or R212, we don't really have, at least I don't have much of a geometric intuition. So it's not really clear what the dot product is doing. But the way we kind of work with it in more dimensions is we just kind of extend the things that work in R2 and R3 and kind of use them as the definitions for what's going on in these bigger spaces. Okay. So in Rn, it's kind of clear what we should do if we want to be consistent at this point. So if we have an X vector with a bunch of pieces and we dot it with a Y vector with a bunch of pieces, you get out exactly what you think you do. So you take the first components, multiply them together. You take the second components, multiply them together, and then you just do that for each piece, and then you add them up when you're done. Okay. And there's nobody to stop you from doing that in 275 dimensions if you want to. Now, one thing I've kind of glossed over, but it's important, it's kind of in the context here, is that to take the dot product of 2 vectors, those vectors have to live in the same space. If you want to take a dot product of something, one vector in R2 and one in R3, you can't. They're just, you're done. Okay. So to take a dot product, the 2 vectors must live in the same Rn. Okay. If they do, it's easy. Okay. How are we doing? So far, so good? Okay.
Pretty straightforward, yeah.
It is. Okay. So let's just do like a simple example before we start going after what this stuff means geometrically. Okay. So example. Let's say I had 1 minus 3, 4, and I want to dot it with something else. Okay. It is simply 1 times 2 plus minus 3 times 0 plus 4 times minus 1. You do all those things, 3 minus 4, and I get out minus 2. Okay. That's your answer. So keep in mind that this product actually spits out numbers. It does not spit out other vectors. All right. Let's do this. So once I've gotten this far, I could then start to get, yeah, let's do this. So if I were mean, I could say something like, for what values value or values of some parameter k is the dot product of 1 minus 3, 4, 2k minus 1 equal to 0. Okay. So what you do is you just drag that k through whatever dot product you have and then set it equal to 0 and solve. Okay. So we have 1 times 2 plus minus 3 times k plus 4 times minus 1. And that gives me what? Bless you. Minus 3k. 2 minus 4 is minus 2. Okay, so that's my dot product. Now I would solve minus 3k minus 2 equals 0. And I believe I get k equals minus 2/3. Okay. So because you end up with kind of a relatively nice simple expression, everything you already know in math can be put to good use by dragging a parameter through this thing or something. Okay. Now let's look at something in ARC2, and I want to start figuring out what this thing actually is telling us geometrically, because it's not obvious right now it's doing anything geometric. Again, it always kind of just really shocks me that all of Euclidean geometry is holed up inside this thing. All right, so if we have x1, x2, let's just look at something in R2. Okay, we have an arbitrary vector in R2. There's my vector x. Okay. So something we've not done a whole ton of, but it's been lurking around in the background. Is if I kind of break this up into my x1 and x2 axis, this piece right here has length x1, and this piece right here has length x2, right? So what is the length of my x vector? Well, Pythagoras, okay, so thanks to Pythagoras, the length of the x vector, okay, and by the way, length of a vector has its own symbol. It looks like a double absolute value sign. That stands for the length of a vector, okay? So the length of this vector must satisfy length of x squared, because that's just my hypotenuse, equals x1 squared plus x2 squared, right? That's the Pythagorean theorem right there. And now I just want to point out that x1 squared plus x2 squared is exactly what I get out when I take that x vector and I dot it with itself. Right? Because the dot product says, look over here, it says take your first two x components, in this case it's x1 here, and it's also x1 there, multiply them together, boom, there's my x1 squared. I do the same in the second component, boom, there's my x2 squared, and I add them up. Okay? So when I take a vector and dot it with itself, what I get out is actually the length of that vector squared. Okay. So in R3, I can do exactly the same thing. You can haul out Pythagoras, and you have an x1 squared plus an x2 squared plus an x3 squared. I'm not going to do it because I think you probably all believe me. So in R2 and R3, this makes geometric sense because of Pythagoras. So in general, we use this to define the length of a vector in general. So in R2 and R3, this makes sense geometrically.
What about in higher dimensions?
Well, in higher dimensions, I don't really have a good sense for what makes sense geometrically. So what we do instead is we just actually use this as the definition of the length of a vector. Okay.
Okay.
So this leads us to define so it's actually a definition for higher dimensions, but it matches the one that we have in R2 and R3. The length of x, okay, equals, sorry, the length of x squared is equal to x dotted with itself, where x lives in any Rn. Okay, so in other words, if we do want the length, we just have to take a square root.
And this
Oops.
double absolute value looking thing means length.
You got it.
Cool.
Okay. Okay. So if I just take a vector and dot it with itself, it's actually not its length, it's its length squared. So if you want to get its length, you have to take a square root. Now, there are a few properties about the dot product. I don't want to spend a whole lot. There's actually a lot of properties. Some of them I'm going to use. I don't want to like unleash all of them on you and say memorize, so because there's no reason you should, but some of them I want you to kind of recognize when you see them again. So there are some properties of the dot product. Let's just say properties of the dot product. And I don't want to prove these just because it's really boring and all you're doing is dragging these things through a relatively straightforward computation and factoring stuff out. Okay. So we have things like if I take x and dot it with y, I get the same thing out if I just did the other order. So it's commutative. Okay, because remember, the calculation comes down to just multiplying the components together, and there the order doesn't matter, so the dot product doesn't care. Okay. It also has some nice linearity properties. So I have x dotted with y plus z is equal to x dotted with y plus, oops, I forgot that, plus x dotted with z. Okay, so I guess if you're keeping track, this one would be commutative and this one would be some type of associative across vector addition. So make sure this makes sense. So y plus z, y and z are both vectors, so y plus z is a vector, and assuming everything lives in the same place, because otherwise we're kind of dead in the water. No, I end up with another vector in Rn that I can dot it with x. Okay. Another thing that happens is that it kind of plays nicely with scalars. So if I have a vector x and I multiply it by a scalar, and I dot that with a vector y, all that has, the only effect that has is it multiplies the entire product by c. For any scalar c. Hang on. Okay. And the last one is if I take a vector and dot it with itself, okay, I get, as promised, the length of x squared. I just want to point out that that is always bigger than or equal to 0. Okay. And there's only one vector that has a length of 0, which would be, go for it.
The 0 vector.
0 vector. Yep. So, and x dot x is equal to 0 if and only if x is the 0 vector. Okay, because what I'm doing, remember, for that length, I'm essentially taking all the components of x and squaring them and getting 0. So if I'm adding a bunch of positive things, because they're all squares and getting 0, sorry, I'm adding a bunch of non-negative things and getting 0, they must all be 0. Okay. Okay. So example. Let's let x be some vector, minus 1, 0, 4. I'm just making one up. Find the length of x. Okay. And you just say, well, I'm just going to dot it with itself. And remember that I don't get the length of x, I get the square back. So that is minus 1, 0, 4. Dotted with itself. And I think I get 1, 0, and 16. So I believe I get 17 out. Therefore, length of x is square root of 17. Hang on. I didn't like my... That's better. We still good?
Yeah.
All right. How are we doing time-wise? 4:47. Okay. So one other property that kind of comes out of these things is if we take some vector x and multiply it by some scalar, how is the length of that new vector related to the length of the x? And it's fairly straightforward, but there's one thing that's easy to miss. Okay. So let me just kind of draw you a picture. So let's say I have some vector over here, x. Okay. What if I then look at 2x? Okay. How are the lengths of those related? That's not a hard question. The length of the 2x is twice the length of the x vector, correct?
Mm-hmm.
Okay. So it is kind of tempting to just write, I'm going to fix this here in a second because it's not quite true, that is equal to c times the length of x. But that's not quite correct, because what if I multiplied my x by minus 2? I wouldn't say the length of that vector is minus 2 times the length of x. Instead of just taking out the scalar in front, I have to take out the absolute value, okay? The length doesn't care about the direction, so in order to fix it, I just have to do that. So what happens if you actually want to go through this proof and drag that c through all those components? Everything in x gets multiplied by a c, and then you're squaring them because you're multiplying them against each other. So you get a c squared that shows up each and every one that you factor out. But then when you go to find the length, you're actually taking the square root of the c squared, which is absolute value of c, okay? Okay. So for reasons that will become apparent later on, it is frequently nice to work with vectors that have length 1. Okay. In fact, they're so nice that they get their own name. They're called unit vectors. A unit vector is a vector of length 1. Okay. So the next procedure I want to teach you is also nice and well, this whole section's nice and easy for the most part. Okay. So given any vector, sorry, non-zero vector, because the zero vector is always special, you can always find a unit vector pointing in the same direction. So given any non-zero vector x, okay, there is a unit vector pointing in the same direction. Okay. Sounds like somebody's on a train. Somebody on a train?
Someone's trying to start
That's
a boat.
someone racing through my parking garage, sorry.
Okay, that's right. It's not you, is it?
It is
Yeah.
not, I don't
Later.
do much racing in my
Later.
Honda Accord.
You never know. Okay, so here's how you can build it, because we've actually already kind of done one. Okay. So for example, So where the heck did that thing come from? I didn't put a line there. Oh, it wrote a triangle. Hang on, I got to turn this setting off because it's driving me nuts now. I was playing with it before. Ink to shape. Here we go. Oh, I didn't know it did that too. Okay. So the example we just did, I don't remember what it was. What was the vector I picked before? Minus 104. So that length is square root of 17. Okay. So if I want a vector in the same direction, what I'm going to do is I'm going to scale that vector that I have. Right now, I happen to know that the vector I'm starting with has a square root of 17. So to get a vector in the same direction with a length of 1, what do you think I'm going to scale by? So this vector is kind of too long. It's bigger than unit length. So I need to make it smaller. So what am I going to scale by? Go ahead and guess.
The length?
I'm gonna take the
The
reciprocal
inverse
of you
of the
exactly
length.
the reciprocal of the length.
Mm.
Okay, so that is not a unit vector. So what I do is I divide, by the length, and I drag this ugly thing through whatever I got to do. Okay, that is a unit vector.
So is it always the reciprocal of the length? Of
Always.
The,
Yep.
okay.
Yep. So I was about to write that down. So in general, again, for non-zero x's, because that's always special, for x not equal to the 0 vector, the x vector divided by its length, and remember that's a scalar, is a unit vector. Okay. In this process of taking a vector and finding a unit vector in the same direction, this is called normalizing your vector. Okay. And vectors of unit 1 are said to be sometimes normalized. Okay. So this is called normalizing a vector. All you do is you find the length of the vector you're starting with, and you go back and divide by it. And again, that's why the 0 vector doesn't work. Okay. All right, let's see. Okay, so far this dot product is kind of getting us some length, and dare I say distance information, because the length of a vector is just kind of its distance, the distance of its the tip of its arrow from the origin. So now let's look at what's called the distance between two vectors. So let's just say R2, because life's a little easier to draw there. Let's say we got one vector X and another vector Y. So the distance between two vectors is exactly what you'd think it is. It's the length of that third leg right there, okay? And what is that vector in terms of X and Y?
Isn't that the product
Easier than that.
or the sum? I thought it was the sum.
Closer, warmer.
So
So X plus Y would end up, so let's see. X plus Y would actually end me up out there, because I'd have
Right.
X, then I have
Oh
Y.
yeah. Okay. Oh, it's the the difference.
It's the difference. That vector right there, okay, that vector right there is Y minus X. Okay. So we define the distance between two vectors. Again, in R2 and R3, this works just like you'd expect thanks to Pythagoras. So in other dimensions, we just define it, the distance between two vectors, to be the length of that distance vector. It's a definition, but it makes sense with what we already know. So we define the distance between two vectors or let's just say between X and Y. And there's notation for that too, but it's easy. D, X, and Y. Okay, D for distance, and you write it like a function, because it is. You plug in two vectors, and this distance function spits out the distance between the two. Okay, and the way we define it is equal to the length of that difference vector. Quick question for you. What happened if I were to do the difference in the other order? What if I did X minus Y?
Different. It would be a different length, right?
You tell me. I'm putting you on the spot.
Would have to,
So
'cause
how is X minus Y related to Y minus X? So let's do down here. Note that if I did the other difference, that's equal to minus 1 times Y minus X, right?
Oh, it's just in a different direction.
Exactly, but it's the same length.
The
So
same length.
if I crank out the length, I get the same exact thing. So the length of X minus Y, go back to that thing there that says how I can actually pull out the absolute value of a scalar, is equal to the length of minus 1 times Y minus X. And that says I can pull out the absolute value of the minus 1 times Y minus X, and the absolute value of minus 1 is 1. Okay.
so if we're getting a negative value, then we're getting a. So if
we're still going to get a
negative
positive
value,
number.
yeah.
We're going to get the same positive number out for the length.
Gotcha.
Yep. Okay. So the distance function is symmetric. The universe would be a lot more interesting if the distance from A to B were different than the distance from B to A. Right? I mean, I guess it is in like big cities where they have one-way streets, but that's a different topic. Okay. This distance function is symmetric. Order does not matter. Okay. Okay, we still doing good?
Yep.
Okay. So this is kind of how the inner product kind of gets involved with lengths of vectors and distances. Next, I want to go at, again, this boggles my mind. Angles are actually involved in the inner product. Okay, so how does the dot product, and just like there are many names for the dot product, there are many notations, okay? One of the more common ones you'll see in like more advanced math classes or physics classes is they use angled brackets. So sometimes you will see that to denote a dot product. Okay. So that's just the same for us as x dot y. Okay. So how does the dot product involve angles? Well, I'm glad you asked. Okay. So let's say we have a couple of vectors here. There's my x. There's my y. Okay. And what I'm really kind of interested in right now is that there's some angle that I shall call theta between those two vectors. Okay, so what I want to do is I want to look at the length of that thing right there. Okay. So in terms of lengths, just notation, what do I have going on here? So this length down here of this side of this triangle is just the length of x, correct? This one up here is just the length of y. And this one right here is y minus x. Okay. So far, so good. So all I did was label my triangles, but I labeled them using this fancy length notation. All right. So what I'm going to do is I'm going to kind of work on this two different ways. I'm going to take this thing right here is kind of the key that I want to work on. Okay. I'm going to work on it as a dot product, something times itself. Okay. On the other hand, I want to figure out how that theta helps determine its length. And I'm not going to stand here and derive the law of cosines for you, but I'll probably remind you of what it is. So the law of cosines tells us, I'm sure you guys are all over this already, right? The law of cosines says that this y minus x vector, okay, is equal to, so it looks like the Pythagorean theorem, sorry, this is a square, I forgot to square it, x squared plus y squared minus, I hope I have room to do this, minus 2 times x, length of x times length of y times law of cosines, so it's the cosine of the angle between them. Okay, that's just a straightforward law of cosines, but using my fancy notation. Okay, you'll probably just want to take my word for it, but you can look it up tonight if you don't believe me. Now on the left-hand side, I'm going to actually write this thing right here using a dot product. So that thing is equal to the y vector minus, so hang on, one more step. So that thing is the y vector minus the x vector. Sorry, that's squared. I keep forgetting that. Okay. Dotted with itself, because that's how we get length. Okay. So that third leg of the triangle, on one hand, it's equal to this weird expression involving a cosine theta. On the other hand, it's equal to the length of that vector, which is that vector dotted with itself. Okay. Now, what I would do it in painful detail, but I know it's going to bore you to death. I haul out those properties that we had before, the symmetric and all this stuff. So when I have a difference dotted with a difference, or a sum dotted with a sum, I can FOIL this thing out just like I would ordinarily, and it works just like you would expect. Okay, so this ends up being, what are all of the things I get? So I end up getting a y dotted with itself. So that's like my first term. My outer term is minus y, because of that minus sign on the x, dotted with the x. The inner term is minus x, dotted with the y. And then last, my last term is minus x times, minus x dotted with minus x. The two minuses do in fact cancel. And I get x dotted with itself. So all I did was I FOILed out that times that. Okay. Now, this right here, y dotted with itself, that's just the length of y squared. This right here, length of x squared. Okay. And remember, the dot product is symmetric. So this y dot, I could go either way with this, but it's kind of prettier to put my x first. So this right here, because it's symmetric, is equal to x dotted, put the dot in the wrong place, is x dotted with y. Okay. So when the smoke clears from this thing, I got to put my x's first or I wouldn't be able to sleep tonight. X squared plus y squared, okay, length squared, sorry. The inner term, I have, basically this is the same thing shown up twice because it's commutative. So I get minus twice, I keep putting my dots on top. This is not a physics class. X dotted with y. That's the left-hand side in terms of a dot product. And I bring this thing down to the right-hand side. So this whole thing must be equal to this mess. Minus 2 length of x, length of y, cosine of the angle between them. Okay. So I kind of cranked out that third leg of the triangle two different ways. Once involving a dot product and once involving the law of cosines. Now those two things are equal. And I got a couple things that just go, they go away. Okay. There I have a length of x squared on both sides. There I have a length of y squared on both sides. I can multiply both sides by minus 1/2 because the 2's kind of cancel. The minus sign cancels. So therefore, what I end up looking at is x dotted with y is equal to length of x times length of y times cosine of the angle between them. That is a beautiful formula that you might want to memorize. Okay. So I did it in 2 dimensions. The same thing works in 3. You just hit, it's exactly the same thing. So again, this is a situation where in 2 and 3, it jives with what we already know. So we actually use this as a definition in higher dimension spaces. Okay. Again, you can't picture them. Okay. So in higher dimensions, so in general, we define the angle between 2 vectors in general, between X and Y to be the inverse cosine of what? So I want to get cosine theta by itself. So I take that X and I dot it with Y and I divide by length of X, length of Y. Okay. And then I go and find the angle that has that as its cosine. Okay. So this is a definition in like 4 or more dimensions, but it comes from the fact that it actually works as we would expect in 2 or 3 dimensions. How are we doing time-wise? Ooh, that took a long time. Okay. I don't memorize the inverse cosine. I memorize the one that I put the stars around. Okay. So this naive little dot product that is so simple that when you calculate it, it's like, oh, this can't possibly be good for anything because it's too easy. It contains both distance information and angle information. Okay, so it contains all of Euclidean geometry inside that one little dot product. So in general, in fancier math, physics, or whatever, one of the ways that you can kind of start messing around with things is you can change what your dot product looks like. And not only can you kind of change it all at once, as you get really fancy and actually say it does slightly different things at slightly different points in your vector, in your space. Okay. So it gets kind of weird, but a dot product pretty much defines your geometry. And the one that we have done here ends up defining Euclidean geometry because that's kind of how we defined it. Okay. All right, so let's do an example. I've been flapping my gums for too long. So example. Find the angle between, let's just pick a couple vectors, 2, 1, minus 3, and 4, 1, 1. Okay, so do me a favor for a second. First, crank out their dot product, and then find the length of each one. It'll take you half a minute, but it's not terribly hard. Quick, what's your dot product?
12.
Yep, that's what I get. All right, what's the length of the 2, 1, 3?
Is it 14?
Close.
No.
Yeah. It's close though.
You multiply it, you dot it with it itself, right?
Yes, but I don't get the length. I get the length squared when I do that.
Ah.
Remember, so the length is actually square root of 14. Okay.
So we're doing 3 then, not -3?
Oh, did I screw up my, sorry, I just blew it. Hang on. Nope.
Oh, it's all good.
What do you want to do?
We're already
no.
doing 3. Let's
Okay,
do it
let's
3.
let's do 3. Sorry about that.
Oh, good. Clarifying.
All right, now see if I can. And the length of the last one, square root of 18?
Yep.
Okay. I'm going to pause because if anybody has any questions about how we did that, ask them now. So for the inner product, I just multiply the three pieces together, 8, 1, and 3, add them up. And for the lengths, I just square each piece and add them up. And that's my length squared, so I want a square root. So for the second one, the 2, 1, 3, I have 4 plus 1 plus 9, which gives me 14. So it's length of the square root of 14. Okay. So the angle between them must be the angle whose cosine is 12 divided by square root of 14 times square root of 18. Okay. Quick, what's that off the top of your head? I'm just
40.
kidding. I have no idea what that thing is. So all I'm going to do is get out my calculator and do an inverse cosine, but I'm going to remember to do what on my calculator? Anybody?
Change it to radians.
Put it in radians. That's right. I don't know how they do
it's
things in
in
those
radians?
engineering classes, but I want your calculators in radians for the math classes. All right, so what do I have? I have 12 divided by, I don't use the square root button very often, divided by square root of 18. Okay, and then I take inverse cosine of that, and I get something that looks like about 0.714 radians. Anybody else? Okay.
Yeah.
Okay. Ooh, time-wise, we're getting down to it. Okay, so one last word I want to introduce after I do this. Where'd you go? Come on. There we go. I was afraid it was telling me it's time to end class. All right, so go back to this thing here for a second. I'm just going to write down what we were looking at again. So x dot y is equal to length of x, length of y, cosine of the angle between them. Okay. If I have two vectors in R2 or R3, if I did it right, those are perpendicular. Okay. What's the angle between them?
90 degrees.
Yep, but in radians,
Oh,
pi over 2, right?
pi over 2.
Yep. So two vectors, let's put it this way. If x and y are perpendicular, theta equals pi over 2. So cosine of pi over 2, in fact, let me just write it as cosine theta. It's kind of a general case here. Oh, I think my computer's dying. I blame whiteboard. Last Tuesday after you guys left, my computer just went, it pretty much died right after you guys left.
Mm.
So just give me 2 more minutes, computer. I ain't gonna do it. Oh, well, whatever. Let's just say all that to change the pi over 2 to a, come on, you can do it. No. All right, well, let me talk you through it. Maybe it'll recover. So if theta is pi over 2, what's the cosine of pi over 2?
0.
0. So if I have two perpendicular vectors and I take their dot product, I get the length of the one times the length of the other times the cosine of pi over 2, and I end up with 0.
0.
So perpendicular vectors always give me a dot product of 0. So cosine theta equals 0. Therefore,
All right.
x dot y equals 0 if and only if X. I'm going to introduce a symbol now for perpendicular because I'm now officially tired of writing the word perpendicular. That's perpendicular. Okay. So again, in 2 and 3 dimensions, this works exactly as expected. So we use this as a definition, or we would if my computer were still working. I'm at 5:20. I just wanted to give me 60 more seconds, I'll be good. So we use this as a definition in general. Only for whatever reason, they don't use the word perpendicular because that's kind of reserved for 2 and 3 dimensions where we can picture things. Instead, somebody had the bright idea that they would use the word orthogonal. You hear orthogonal, just think perpendicular. So in general, we say X and Y are orthogonal. Okay. And we write that symbol that I just told you guys. Okay. If their dot product is 0. Okay. So again, in 2 and 3 dimensions, this matches exactly what we'd expect. So we use this as a definition for other dimensions. Even if you're not talking about physical dimensions, if you're talking about logical dimensions where, you know, your vector space, whatever you're doing computer-wise might have, I was looking at the Titanic problem the other day. So you might have like gender, age, socioeconomic status. You might have these weird logical dimensions. It still kind of makes sense for things to be orthogonal. And what that means is that they are kind of pointing in different logical directions.